Chem 106, Chapter 16, Acid, Base, and Solubility Equilibria, Lecture 1. A review of acids and bases. There are three main models of acids and base theory. The original was the Arrhenius model. It's an older, very limited definition of acids and bases, wherein acids are substances that produce hydrogen ions, and bases are substances that produce hydroxide ions in aqueous solutions. The picture is more complicated than that, though. And another model, developed by both Bronsted and Lowry, in different countries, but somehow simultaneously in history, they both came up with and published their models of how acids and bases function. And so what they want to do is define it a little more carefully, that acids are hydrogen ion donors. A hydrogen ion is also called a proton because isotopically, almost all of the hydrogen on this planet is of the isotopic variety called protium. Protium is the isotope of hydrogen that has just one proton and one electron, but zero neutrons. And so we can just say that a hydrogen ion, where you remove the electron, then essentially is just a bare proton. But please know, even though we can write H+, we don't really mean H+. It has to be bound to something. You can't just have a bare proton, not in chemistry anyway. Nuclear physics maybe, but in chemistry not. And so we'll still call them protons, the hydrogen ions, just because it's a term we commonly use. But do know that you should never really see H+ by itself except to say that it is a hydrogen ion. It's understood that in aqueous solutions it's always bound to some other molecule. Bases then are proton acceptors. So an acid is going to give away a hydrogen ion. A base is going to take on or accept or receive a hydrogen ion during a chemical reaction. The Lewis model of acid-base terminology has that the acids are electron pair acceptors and bases are electron pair donors. This model, Lewis's model, is really the most general, most useful model. And when you get to organic, if you're taking organic chemistry, the Lewis model will prevail in terms of how chemical reactions happen for organic molecules, even though you will still use some of the concepts of Bronsted-Lowry model for certain ideas of how things happen. But by and large, Lewis, and we will talk about this later also, but the Lewis model is the prevailing model of acid-base technology. But this chapter, of course, we're going to focus on Bronsted-Lowry theory and a lot of details associated with it. So if we extend this idea then, we can talk about how many acidic hydrogens are on a particular acid. If there's only one acidic hydrogen, which by the way, acidic hydrogens are always written first on the molecule for acids, unless they are organic amines, which have been protonated. But I'll explain that in a little bit. But by and large, when we're talking about acid molecules, acidic hydrogens are written first on the formula. So if there's one acidic hydrogen written on the front of a formula, we call that a monoprotic acid. If there are two acidic hydrogens written on the front of a formula, then it's diprotic. If there are three acidic hydrogens, then it's triprotic. But really, even from two, or more, we can just use the prefix meaning many, which is poly, and so we can say they are polyprotic acids. So it just depends on how careful you want to be. But in generalized terms, if there's two or more, they are polyprotic. A term in use also is amphiprotic, which is similar to another term you might have heard, amphoteric. But all it means is that a particular substance can act as either an acid or a base. Amphiprotic can either donate or receive a hydrogen ion. When we do acid-base reactions, then, we can have conjugates, or we do have conjugates. If you have an acid and a base on the reactant side, on the product side of the equation, you're going to generate a conjugate acid-base pair. Now, just in general definition, a conjugate acid-base pair consists of two species that differ from each other only by a hydrogen ion. If they differ in any other way besides a hydrogen ion, they are not acid-base conjugate pairs. But what we can say then is that a conjugate acid is the protonated species on the product side of a chemical equation that was originally the base on the reactant side. A conjugate base is the deprotonated species on the product side that originally was the acid on the reactant side. And so what we can do then is, using Bronsted-Lowry terminology for acid, base, and conjugate pairs, let's look at the lecture problems for this and solve a couple of things here. And looking at number 1, the first reaction that we have is HC2H3O2 aqueous plus H2O liquid is in equilibrium with C2H3O2 minus aqueous plus H3O plus aqueous. Okay, so what we can do is we can label the 4 parts of this equation, and that's what it says. Identify the acid, the base, conjugate acid, and conjugate base in each of the following chemical equations. Okay, so the way we can do this is, you already know HC2H3O2 aqueous is acetic acid. Well, that must be the acid. But do it logically. When you look at it, we can look at each side of the equation in terms of what the more or less important atom is. So let's say here's the carbon species, because there's no carbon over here, but the acetic acid has carbon in it. So look at the carbon species here on the reactant side. Look at the carbon-containing species on the product side. Notice that the carbon-containing species on the left, on the reactant side, has a hydrogen out front, whereas the carbon-containing species on the right, on the product side, does not. That must mean that the species on the left must have given away a hydrogen to get to be the species on the right. If it donated a hydrogen ion away, then it must be, by definition, the acid. That must mean the other substance in the reactant side is the base, but still, let's go through the logic of it. If we look at this oxygen-containing species, water, if we look at the oxygen-containing species on the left, it has 2 hydrogens. If we find the oxygen-containing species on the right, it has 3 hydrogens. That must mean the oxygen-containing species has accepted another hydrogen. There's 3 on the right, but only 2 as it started on the left. If it has gained a hydrogen, then it must be, by definition, the base. Then we can get to the conjugate side. What was the acid? The carbon-containing species was the acid, so that must mean then it is the conjugate base. Then what was the base? The water, the oxygen-containing species. On the right, the oxygen-containing species must then be the conjugate acid. All right, so there's the 4 parts for that one. Let's look at the next one. Here we have ammonia, aqueous, reacting with water, liquid, in equilibrium with ammonium ion plus the hydroxide ion. Okay, label the 4 parts again. Here we have a nitrogen-containing species and an oxygen-containing species. So let's focus on the nitrogen since it's first in our list. On the left, the reactant side, the nitrogen-containing species has 3 hydrogens on it. On the right, the nitrogen-containing species has 4 hydrogens on it. That must mean it must have gained a hydrogen from left to right, and if it gained or accepted a hydrogen, that must mean that it is a base. Now that means, of course, then the other species must be acid, but still do it logically and completely. The oxygen-containing species on the left, the reactant side, has 2 hydrogens. The oxygen-containing species on the right, on the product side, has only 1 hydrogen. So it must have given away or donated a hydrogen, which makes it, by definition, the acid. So now, what was the base, the ammonia, the ammonium, the nitrogen-containing species on the right, must be the conjugate acid. And, of course, then, what was the acid on the product side must become the conjugate base. The oxygen-containing species was the acid, so the oxygen-containing species on the right must be the conjugate base. Okay, now, as an interesting note, notice that the water in the first reaction functioned as a base, but in the second reaction it functioned as an acid. This must mean that water is an example of an amphiprotic substance, because in the first one it gained a hydrogen on the product side. In the second reaction it lost a hydrogen on the product side. So it can go either way. It can go from both sides. Amphi means from both sides. So it can either accept a hydrogen ion or donate a hydrogen ion, depending on which situation it's in. Okay. Let's look at the next one then. Number 2. For this one, what is the conjugate base of each of the following species? Okay. So, for A, we have HCHO2. This compound is called formic acid. It's the simplest of the organic acids. But what we care about here is, what is the conjugate base? Now, if we're saying conjugate base, that means it must have 1 less hydrogen than this. Because remember, the difference between a conjugate acid-base pair, the only difference can be a hydrogen ion. And so if we have the conjugate base of something, that must be its deprotonated version. If we have the conjugate acid of something, that must be its protonated version, an extra hydrogen ion. So if you get a formula and you're asked for the conjugate base, then you take away a hydrogen ion. So I'll even write this on this as minus H+, just so we can see for sure. If I take away, it's going to be the H out front, because remember, those are the acidic ones. So I'm going to write CHO2. And now this was neutral out here as a charge, and I took away a plus. So that means this must be a 1 minus then. So HCHO2, the conjugate base, must be CHO2 minus then. Let's do another to make sure we have this then. If I have the monohydrogen phosphate, remember the names on these. It's important that you know the names of these. Monohydrogen phosphate. Again, I want to know what the conjugate base is, which means I need mechanically to remove a hydrogen ion. When I do so, again, I'm going to take that hydrogen ion off of the front and leave only the PO4. This was a 2 minus, and I'm taking away yet another plus, so that becomes 3 minus. So functionally, the conjugate base of monohydrogen phosphate is just phosphate. Let's look at it going the other direction then. Number 3, what is the conjugate acid? So here in the first one, I have SO4 2 minus. That's sulfate. Functionally, to make the conjugate acid, I'm going to add an H plus to this. And when I do, that means I just put an H on the front of it and write the formula, SO4. And now it's an 2 minus, but I'm putting a plus on there, so that has to reduce it to a 1 minus. So you put the H on the front and then reduce the charge by 1. So SO4 2 minus becomes HSO4 1 minus. Another example, and this one's a little more complicated, because remember I mentioned a little while ago about organic amines, that whenever we are going to add a hydrogen to it, it has to go on the nitrogen. So let's start off with this compound, that we start off with what's called methylamine, CH3NH2. And what we want to do is we want to have the conjugate acid of this. So that again functionally means that we are going to add an H plus to it. But now we don't stick it out on front, even though we could though. And it wouldn't be wrong at this level to put it just on the very front out here before the C and say that's it. But really, you guys should be becoming a little more sophisticated. Whenever there's a nitrogen which has a lone pair of electrons, that's what does the work here for the hydrogen ion transfer. That H plus is now going to be bound to the nitrogen in this formula. So we still write CH3. But now the NH2 that was over here on the left is going to become NH3 because we're gaining a hydrogen. The charge out here on the methylamine itself was 0, and we added an H plus, so that must mean that this now has a plus charge. So what was neutral now becomes a plus charge. So methylamine, CH3NH2, when we add the acidic hydrogen, because it's an amine, AMINE, it's an amine, the hydrogen goes with the nitrogen whenever we add it on, because the nitrogen is the basic part of the molecule. So that's what's going to accept the hydrogen. All right, so now we have those. Going back to the outline, let's talk about what water does. Water and the pH scale. Even the purest of water, freshly made, you just distilled it, whatever, freshest made water ever, is still not pure water. It immediately auto-ionizes. Auto is a prefix meaning self. Water reacts with itself to form ions. And so in pure water at 25 degrees Celsius, 2 molecules of water are going to react to form H3O plus and OH minus. You see the 2 water molecules, when they react, one is going to accept a hydrogen and one's going to donate a hydrogen. Let me show you a picture of how this looks. Just because if you're going into organic chemistry, this will give you a preview of what we call mechanisms and how you're going to show how things happen. So let's say graphically, I have 2 water molecules. There's one. And here's the other. In any sample of water, remember there are trillions, way beyond, 10 to the 23rd in a mole, molecules of these water molecules running around. And so every once in a while, even in the purest of water, what's going to happen is that a lone pair from one of the water molecules is going to bump into the hydrogen of another water molecule and take it. The electron pair, remember the lines represent a covalent bond, which is 2 electrons. That electron pair stays with the oxygen though. So we have, again, a lone pair of electrons on one water molecule is going to bump into a hydrogen atom on another water molecule and take it with it and leave behind the electrons that stay on the original O. So now what we have are 2 molecules where we have the hydrogen ion version, which now, because it is a charged particle, we put it in parentheses and put a plus out front of that, and brackets, not parentheses. All right, then the other water molecule that now has a lone pair where it didn't before, and again put this in bracket and have a minus out in front of it, because what we find mechanistically happens is whenever we have a chemical reaction, what was a lone pair becomes a bond. What was a bond becomes a lone pair. So all we did was transfer this hydrogen from one molecule to another. Because it didn't take any electrons, it went as an H plus. And so a pair of electrons that was a pair of electrons on this water molecule originally now becomes a covalent bond because it's sharing those electrons with that H plus. what were the electrons that were being shared with it before now just becomes another lone pair of electrons on the molecule. All right. So back to the outline. We can see then two water molecules that are liquid are going to react with each other to form a hydronium and a hydroxide. And now because it is exactly that way in solution, all the rest of the molecules are water, and it takes two water molecules to produce one hydronium and one hydroxide. Hydronium and hydroxide concentrations are the same. In pure water at 25 degrees Celsius, the concentration of hydronium and hydroxide is 1.0 times 10 to the minus 7th molar. If we change the temperature, that's why I specified this, if you change the temperature significantly, this autoionization changes also, so these values become different. For all that we do in this chapter, we will stay then right at around 25 degrees Celsius so that these numbers mean something. And so you need to memorize this then, that in pure water at 25 degrees Celsius, hydronium equals hydroxide at 1 times 10 to the minus 7th molar. So now we can write a K expression from this, and because water is liquid, it does not get added into the expression, so the expression for K becomes hydronium times hydroxide. That gets a new designation with a W under it, because it's specific to pure water here, or to water at least. And so Kw, the autoionization constant for water, equals hydronium times hydroxide. Numerically then, at 25 degrees Celsius, 1 times 10 to the minus 7 times 1 times 10 to the minus 7th becomes 1 times 10 to the minus 14th. And no, again, K has no units, so even though that should be like molarity squared, it isn't. The units just magically go away. And so the Kw is 1 times 10 to the minus 14th. This is a value in all, an equation and value you must commit to memory because you will need these for the exam and you won't have a cheat sheet, at least not legally. And so Kw equals hydronium times hydroxide, and for pure water, we're going to change that. Let me say that again. Kw is hydronium times hydroxide, and that will always equal 1 times 10 to the minus 14th. But what you see mathematically then, if I do change by adding a solute in, if I add a solute that increases the hydronium, hydroxide goes down accordingly because this is a constant. If I put in a solute that increases the hydroxide ion concentration, hydronium decreases as a result to keep K constant at 1 times 10 to the minus 14th. All right, so what we can do then is we can say that if hydronium equals hydroxide, then it's going to be 1 times 10 to the minus 7th molar. But if we add a solute in that increases the hydronium, then that's going to go up and hydroxide is going to go down as a result. If we add in a solute that increases the hydroxide ion concentration, then hydronium is going to go down as a result. We use this fulcrum, if you will, of 1 times 10 to the minus 7th that we're going to revolve around here. And so what we can do then is we can take these numbers, which are not very friendly, and we can apply a logarithmic scale to them. We'll use base 10 for this, not the ln like we did in kinetics, but we're going to use the base 10 scale, log, for this, and that'll turn these numbers into something a little more familiar. So the equation for doing this is that we take the negative log of the hydronium. The negative out front is arbitrary. Anytime you take the log of a number less than 1, you end up with a negative number, and we want the pH scale to be positive, so arbitrarily we just multiply it by -1 and all values become positive. All right, so pH is going to equal negative log of hydronium ion concentration because pH means power of the hydrogen ion, power meaning logarithmic power of the hydrogen ion. And so if you're given hydronium concentration, you can calculate the pH by applying that equation. If, however, you are given the pH and you want to know the hydronium ion concentration, you simply apply the inverse log to the negative pH. And we'll do a lecture problem with this, so you'll see. POH might be a new concept. But again, if we just have the hydroxide ion concentration and we take the negative log of it, that gives us the power of the hydroxide concentration. And if we want to know if we want to know hydroxide ion concentration if we're given POH, then you simply do the inverse log of the negative POH. All right. So now, again, we can play with this, and we can see that if we have the Kw expression, Kw equals hydronium concentration times hydroxide equals 1 times 10 to the minus 14th, if we just apply the negative log all the way through that thing, then that becomes pKw equals pH plus POH. Remember, if these were multiplied and you apply logarithms, then they become a sum. So pKw equals pH plus POH becomes 14. This is another equation you must commit to memory because you're going to be responsible for being able to use it on an exam without any other written notes. So pKw equals pH plus POH equals 14. Again, we revolve around this 14. So if the pH goes up, the POH must go down. If the POH goes up, the pH must go down, because they all revolve around 14. So then we can say solutions with a pH that are less than 7, that has a pH less than 7, are acidic. Solutions that have a pH greater than 7 are basic, or another term is alkaline. Or if somehow the pH equals 7 exactly, then it is said to be neutral. All right, so let's look at the lecture problems again. Number 4. And you have a table to fill in. And so we can look at this then and see what we're given, and then see if we can calculate the other values out of it. So, let's start with black here. And so there's pH, there's POH, there is hydronium, there is hydroxide, and then acidic or basic. All right. So we're given in the first row, because this goes by rows, don't look at columns, we're looking at rows. In the first row, we're given a pH of 5.25. So then what is the POH? All right. So again, we know then if pKw equals pH plus POH equals 14, then POH must equal 14 minus the pH then. 14 minus 5.25 gives us a value of 8.75. All right. So then, getting rid of all this. Give myself some room to work here. Now it wants to know the hydronium ion concentration. And we know the hydronium ion concentration. Oops. Sorry, wrong color again. Change back here. All right. Hydronium concentration is 10 to the negative pH, which is going to be the inverse log. So second log on your calculator, and you're going to use your plus minus key to get the negative of the pH, and the pH here was 5.25. When you do this, then you should end up with a result that, of course, remember here, there's 2 decimal places in this, and we're going to apply an inverse log, which means you must have a total of 2 significant digits. When you do so, you'll have 5.6 times 10 to the minus 6th, and because it's a molarity concentration, you better remember to put that molarity unit on the end of it. All right. Now we want the hydroxide concentration. So all I only have to do is erase strategic part here. And so if I want, oops, forgot to change again. One there, okay. And so if I want the hydroxide ion concentration, it's going to be 10 to the negative POH, which we already had there. So that's going to be 10 to the negative 8.75. And again, 2 decimal places means 2 significant digits. And so when you calculate this on your calculator, you should get a rounded answer of 1.8 times 10 to the minus 9. And don't forget, because it's concentration, to put molar on there. 1.8 times 10 to the minus 9 molar. Then finally, it wants to know, is this acidic or basic? The pH is what you're going to use to tell that. And the pH here is 5.25, which is less than 7, so it must be acidic. All right. And now you can work through the other lines of it and ask me if you any questions you have about those. But here, let me put, just so you have the data. All right. So originally I gave you 525 for 1, 2.02 for there, 4.4 times 10 to the minus 10th molar there, and 8.5 times 10 to the minus 2 molar there. All right, because now with the rest of the table, all you're going to do is work through the values. And so we already said this was 8.75, 5.6 times 10 to the minus 6th molar, 1.8 times 10 to the minus 9th molar, and of course acidic. All right, when you work through this then, the answers you should get are a pH of 11.98 for the second row, 1.0 times 10 to the minus 12th molar there, 9.6 times 10 to the minus 3 molar there. And again, since the pH is above 7, this solution is basic. Third row. If you're given hydronium, you can calculate pH by doing the negative log, right? And you should end up with 9.36 as the pH. Then doing POH for that gives you 4.64. And then the hydroxide concentration, 2.3 times 10 to the minus 5th molar. And again, the pH was above 7, so it must be basic. Last row. The pH for that one, you should get 12.93. The POH, 1.07. The hydronium, 1.2 times 10 to the minus 13th molar. And of course then, pH, wow, is way above 7. Definitely basic again. Okay, on that last line, because I gave you hydroxide, you would use that to calculate the POH, and use the POH to get the pH, and then the pH finally to get the hydronium. So hopefully there's no questions, but if there are, as always, I am completely available by email or in class or office hours to answer any questions you have about these first 4 lecture problems or anything we've talked about in this lecture. This concludes Lecture 1.